Welcome back after the short break on the topic of linearization of input output transfer characteristic. So, we are discussing about this small signal equivalent circuit. We are about to start that, and the intention there it is of course, to get the simplified circuit. So, you may recall the equivalent circuit if I consider the large signal behavior, what we said it is, and the transistor may be replaced by a current source, dependent current source, and this current source it is capital I d s, which is function of capital V g s and V d s. So, that is what we have discussed, and the V g s it is whatever the voltage it is appearing across gate to source, and then we do have the so this is the device part, and so this V g s is controlling this current source, and then we do have the R d part, and this is connected to V d d. So, this is the V out, the voltage coming here it is capital V out, and the voltage you are applying here it may be having a small signal part along with the DC part. So, we are talking about this is capital V G S, and this part we are talking about small v G S. So, these two together it is defining the capital V G S. So, this model it is referred as large signal equivalent circuit, and so this model it is large signal model of the transistor, and the whole circuit it is large signal equivalent circuit. In contrast to that, whenever we are doing the linearization, what we are doing is we are simplifying this current equation, namely the drain to source current we are considering only the small signal part, which means that small I d s, which is having an expression like one of the three expressions are 2 I capital D s k W by L into V g s. Okay. And what is the V g s? V g s is the voltage across the gate to source, and this V g s of course, it is the small signal V g s, and at the gate we are considering only the small signal part, whatever the V g s we do have or V g we do have, that part, and then of course, we are retaining the resistor, but then at the end of the other end of the resistor we are connecting this to ground, which means that we are dropping the DC part. For the supply we are dropping this is 0, and also this V g s part we are removing here, and then the corresponding whatever the circuit we are getting here, it is small signal equivalent circuit. So, this is what the small signal equivalent circuit. And so, this is the of course, the corresponding output will be observing here, it is showing only the small signal output voltage. So, now you can see that this circuit it is of course, it is simplified, and most important thing is that the linear relationship between this V g s and the V out, it can be directly obtained by analyzing this circuit. So, that is what it is referred as small signal equivalent circuit. One important thing is that whenever instead of say this model, so I should say this is the this portion is the model of the MOS transistor, this is referred as large signal model, whereas in the small signal equivalent circuit, whatever the small signal equivalent circuit we obtain for the transistor, it is the small signal model. So, this model it is small signal model. Now, if you see in this model and this model, here we do have one factor. So, this factor it depends on the size of the transistor, it depends on the device parameter, it depends on the operating point also. And so, if I say that this is one parameter called GM, why GM? It correlates the VGS to IDS. So, it is conductance. So, that is why G, and M stands for trans mutual from input port to output. So, that is why this parameter it is referred as transconductance of the device, particularly for the small signal. And this is one of the important parameter. So, whenever you are talking about the small signal model of the device, it involves one new parameter or new set of parameters rather, and one of them is this GM. So, whenever you are talking about small signal equivalent circuit or small signal model, we require new set of parameter. So, in the while you are going from large signal equivalent circuit to small signal equivalent circuit, first thing is that we need to drop the DC part, and also we have to get this model involving new set of parameters. So, let us see what are the other parameters are there along with this GM. And very important thing is that this small signal parameter, it is a function of the operating point, or it depends on the operating point. So, as just now I said that the small signal model of the device, which is having this IDS as function of VGS, and then it is having this parameter GM. And what is VGS? The voltage appearing across this gate to source. So, this is the gate terminal, this is the drain terminal, this is the source terminal of the device. Now, of course, if I add the rest of the things, namely the resistance RD, and then if you make the connection to ground, if you make this to AC ground, and then if you also draw the stimulus, input signal stimulus, then that gives us the small signal equivalent circuit. But if I for generalization, if I concentrate this part, this is one important information, what is referred as small signal model of the device. And the small signal model of the device GM, actually it is defined in this way: variation partial derivation of the IDS with respect to VGS. So, if I say that the circuit is linearized, so you may say that this part it is nothing but the small signal IDS, likewise this part it is VGS. So, in fact, this representation and this definition actually they are same, and the expression of the GM as we have discussed, one of the form it is square root of 2 IDS k W by L. So, this is one form. This is also same as k W by L VGS minus VTH, and also it is having another form 2 IDS divided by VGS minus VTH. So, out of these 3 forms, whatever the forms you consider, all of them are actually essentially representing this GM. So, this GM may be having different expression. In fact, this expression you can directly you can obtain by considering this definition of this GM. So, if you put the expression of this IDS, and if you say that IDS is changing only with the VGS, that is the meaning of this partial derivative, and from that you can directly obtain these expressions. It involves a small approximation, but actually eventually you will be coming to this point. So, say for example, if I consider variation of IDS, and IDS it is k w by 2 L VGS minus VTH square into 1 plus lambda VDS with respect to VGS. So, what we will be getting it is you are almost getting this one, except this VGS it will be small VGS, whereas we are using capital VGS, and then 1 plus lambda VDS part. So, we can say that this is well approximated by k into w by 2 L capital V GS minus VTH into 2, this 2 it is also coming. So, this 2 and this 2 are getting cancelled out, 1 plus lambda VDS part it is there, and this part you can take it to be 1, and small VGS part we are taking capital VGS, and hence we are obtaining this one. Now, if you use the expression of this IDS in terms of VGS and W by L, and probably then you can replace this VGS in terms of either IDS, or this W by L you can replace in terms of IDS and VGS to get these 3 forms of the GM. So, what we like to say that this new set of parameter GM, it is important thing is that whatever the forms are there, each of these forms are having indication that this the value of this GM it is directly function of this the operating point, either IDS or capital VGS or capital IDS and VGS. So, this parameter of course, it may its value it may vary if you change the operating point. So, to get steady operation, steady linearized operation, whenever you are talking about linearization of the transfer characteristic with respect to q point, it is better to keep this q point constant, so that the value of this GM you can assume to be constant. But in case if it is varying slightly over this linear range, still you may approximate that this is remaining constant. Mathematically you may say that that is equivalent of saying that small VGS and capital V small VGS is same as capital V capital GS. That means, at this point and this point, whatever the parameters are there, essentially they are same. So, this is one small signal important parameter, and we also have another important parameter. So far we are ignoring this 1 plus lambda VDS part, which means the dependency of the this current on the output voltage. So, if you consider that, what we will be getting is that of course, this IDS is dependent through this 1 plus lambda VDS part. We may get drain to source 1 conducting element, and that conducting element is nothing but the output conductance or drain conductance. So, its definition is again here it is partial derivative of IDS, but with respect to VDS. So, if you use this equation, same equation, you can find the expression of this one. So, Please keep that in mind, and once you consider this GD, this GD actually from drain to source one conducting element. So, let me get the expression of this GD, and then again we will be coming back to the small signal model of the device. Probably I do have a different slide for that. Okay. So, it is basically it is a similar thing here, but let me discuss on this. So, we already have discussed this one. Now, we are going to discuss the expression of GD, and that we are getting from this definition, and this IDS, it is having an expression, it is K W by L, rather 2L VGS minus VTH square into 1 plus lambda VDS. So, this is the current expression, and now if I take derivative, basically whole thing. So, we are taking partial derivative of this whole thing with respect to VDS, and if you do so, what we are getting is, so we are not changing this part, we are changing now VDS part. So, we can say this part is constant, namely K W by 2L VGS minus VTH square into lambda. So, you may say that this is well approximated by, so this part if I multiply with 1 plus lambda VDS part, and then if I divide by 1 plus lambda VDS part, then what we are getting here, it is this part along with this we are getting IDS, and then in the denominator we do have 1 plus lambda into VDS. So, this multiplied by lambda. So, in fact, this is normally this part it is considered to be very small. So, we consider this is in fact, I should say this is not approximation, this is exact. Whenever we are coming to this approximation, we are dropping this part. So, this is I ds into lambda, and further to that we may say that this is capital I ds into lambda. So, that is the expression of the output conductance, drain conductance, lambda into IDS. Again, here also you can see that it directly depends on the operating point. We may draw the circuit. Of course, this is the expression of the GD, but we may draw the circuit either in the form of conductance or in the form of resistance. So, then the corresponding resistance, it is just reciprocal of this part, namely 1 by GD. So, the small signal model of the device, the transistor, we can say that it is the current source, which is I ds equals to Gm into VGS, and in parallel with that we do have the conducting element GD, and then we do have the at the input we are defining the VGS, gate to source voltage. So, this is the gate terminal, this is the drain terminal, and this is the source terminal. So, what we are now up to, that we started with linearization of the nonlinear circuit, and while you are doing the linearization, we are dropping the DC parts, and finally, we obtain different equivalent circuit of the whole circuit, and that invites us to consider equivalent circuit of the MOS transistor, and this equivalent circuit involves only the small signals, and that is what the completion of the small signal model. So, this model, of course, it is I should say it is simple enough, but then if this model it is sufficient for mid frequency range and low frequency range, but if you are going to higher and higher frequency, then gate to source there will be some more components, namely gate to source capacitance, then gate to drain capacitance. So, those are the additional elements, again they will be popping up. So, gate to source we may be having capacitance. So, it is denoted by CGS, like gate to drain there will be another element, capacitive element represented as CGD. So, if I consider these capacitive elements, then this model, of course, it is small signal model, but this model can represent the circuit the device behavior in the high frequency range also. So, if I add this capacitive element, then it is called small signal model of the MOSFET in mid frequency as well as high frequency. So, just to simplify, it is normally referred as high frequency small signal model. On the other hand, if we drop these two capacitive element, it is simply said it is small signal model of the MOSFET. So, what may be its application of this model? Of course, we can simplify the analysis and then we can find the gain of this circuit. So, let us consider one numerical example just to highlight that. So, the same example will be going there, but let us start with this new slide. So, just to get some number here, let you consider this device parameters and then the DC voltage and this DC voltage and the VTH and the RD. And what we have to do here it is we need to find what will be the this V out. So, we need to find what will be the V out in terms of this VGS or V in. So, this is same as V in also. Now, let you consider what are the parameters are given to us. It is say this is 10 volt. Let you consider this is maybe 2 volt, and let you consider VTH equals to 1 volt for simplicity of calculation, and then W equals to say 10 micron, L equals to say maybe 1 micron, and let you consider K the transconductance parameter, K equals to say 200 microampere per volt square. Okay. Then we can find what will be the output, but of course, we require the resistance value here. So, let me take how much probably 4K it will be good. Let us see. Okay. So, how do you proceed? First of all, to get the gain, namely, okay. So, what we have to do, the statement is that we need to find our objective is to find V out by V in and its value. So, to do that, how do you proceed? First of all, the small signal parameters, they depends on the operating point. So, first thing is that we need to find the operating point, and to do that what you do, let you consider the DC part. and let me find the IDS. So, IDS equals to K by 2 W by L VGS minus VTH square and then 1 plus lambda VDS. So, for the time being, let you consider lambda is very small. So, approximately equals to 0. So, what we are getting here, it is 200 into 10 to the power minus 6 divided by 2 into W by L. VGS is 2 minus VTH, and square this part it is approximately 1. So, that gives us 1 milliampere. So, that is the IDS DC current. So, the DC current flowing here, it is 1 milliampere. So, the drop across this resistance it is 4 volt. So, from that we can say that the V out, so that gives us capital V out, it is 10 volt minus 4 into 1. So, that is the 6 volt V out, the VDS is 6 volt. Now, we can verify whether the device it is in saturation region or not. So, we do have 2 volt here, we do have 6 volt here. Obviously, the device is having pinch off happening at the drain end. So, the device it is in saturation. Now, then we can find the value of the small signal parameters. So, since we are considering lambda is equal to 0, so we can say that directly we can say that GD it is small, I mean it is 0, and then GM. So, GM it is having different expression. So, either we can write in terms of IDS and VGS minus VTH. Say for example, if we consider 2 times of IDS divided by VGS minus VTH. So, that gives us 2 into 1 milliampere divided by 2 minus 1. So, that is 2 milliampere per volt, right. And then what we said is that GD it is 0. So, that GD is 0. So, that gives us the output voltage V out is R D, of course, with a minus sign, R D into the GM into VGS. So, from this one what we can find is that this is it becomes minus R D, that is 4 K, and then GM it is 2 milli. So, that gives us the gain of 8. So, that gives us the final gain of the circuit. So, so what we have done is that first we obtain the operating point here, and then after that we obtain the small signal parameter value. So, the small signal parameter values are here, and then we obtain the small signal voltage gain by considering this one. In fact, we can draw the small signal equivalent circuit, whatever we already have discussed. This part it is not there. So, this is this I should say G D equals to 0. So, this is for the MOS transistor, and then we do have the R D part. This is connected to ground, and then this is VGS we are applying here. The current here it is GM into VGS. So, the voltage appearing here appearing at the output node here it is this current multiplied by this R D. So, that is why we say that V out is this one. I think probably you can try to make similar attempt in case if the circuit is different, namely if the circuit is containing PMOS transistor, and then you can see what may be the corresponding small signal model and so and so. I think that is all I need to discuss, but let us see what are the things we have covered so far. So, today we have discussed about linearization of a nonlinear circuit containing MOSFET device, and then we have discussed about the small signal equivalent circuit. So, whenever we are talking about linearization of the circuit, is basically we are translating the actual circuit into small signal equivalent circuit, and then in the small signal equivalent circuit, whatever the circuit we are having corresponding to the MOSFET, it is referred as the small signal model of the MOSFET, which involves different set of parameters, namely say transconductance Gm and Gd, and their values, of course, it depends on the center point of the linearization, namely the quiescent point. And then what we have seen is that if you use this small signal model of the device in actual circuit, that will simplify the analysis, and also that will simplify the calculation. In fact, in today's simple examples, the simplification you may or may not appreciate, but whenever it involves a circuit having many transistors, I am sure that then you will appreciate the utilization of the small signal model of the transistor. I think that is all I do have. So, thank you.